So, just because I missed I cut the first bit off because I was recording over myself. But what I'm saying is we're going to talk about the low-level primitives that comes about with cloud computing. That is to say that we abstract so much of the technical complexities of a data center that I want us to get to grips with what happens when I go online, when I check out a bit of software or any of those things ultimately, and really this entire infrastructure that somehow connects you, the person or the people in this case, with whom we're connecting to. So what we're talking about is IT technologies or cloud computing, networking as a whole, okay? Well, it turns out there's actually a whole stack of things, of internet technologies that underlie the software that you and I are currently using nowadays every single day. And indeed, the software that we use, the likes of browsers, clients, email clients, and stuff like that, are really just abstractions, very friendly abstractions of some low-level primitives and implementation details, which I hope we can to get to. So, ultimately, at the end of the day, we have built these abstractions on top of those, better known as, say, the cloud, which is just an abstraction on top of that underlying infrastructure that enables us to do most of anything we want to do computationally without even having to do so from our hardware locally. So for new people, what I'm going to get to is just this phrase, which you'll hear time and time again. There's no such thing as the cloud. It's just someone else's computer. Almost emblematic at this point. There's no cloud, just someone else's computer. So for my newbies, it's somewhat true. To some extent, it could be argued that it's no such thing as a cloud at all. It's actually all underwater because of undersea cables, discussion which I hope to pick up in just a second. But so I want to see if we can distill what goes on when you type into an address bar, a URL bar, into the address bar for search bar, and you hit enter. Or when you type out an email, you say someone's email address and you hit enter. What's actually going underneath the hood there? So at the end of the day, what happens is when your laptop, when my laptop or our desktops actually try to talk to each other, even our servers are capable of really, is just sending messages back and forth to one another, in what we're going to call teeny tiny little virtual envelopes. Daniel, I'm still in the way. That's really rubbish. I don't know why that's happening. Well, thanks for sending me. You know what? It's fine. If as long as I can get in the way. Kind of not so good, but why does that happen now? 2 seconds, people. Let me just see if I can fix this, remedy this somehow. If I stop sharing, can you see me now? Can you currently see my face? You can, can't you? Yeah, because obviously you see my screen. But what happens if I do this? Okay, what happens if I do this, though? 2 times. Probably 1 time now. Can you see my screen? Can you just see one marker now? Better, says Najma. So sorry, but what happened was I inadvertently just did the exact same thing last time. Bingo. All right. So trying to get data from point A to point B, which is what I'm trying to do is really just communicate online, trying to tell you, or like you're trying to tell me that there's a problem online. Well, we're going to do that via relays and communicating from point A to point B, which is really just sending some kind of little TCP/IP packet, some kind of data envelope sent from back and forth, which I'm going to represent as kind of being an envelope, so to speak, which an envelope is you can think of in the real world. And the analogy I like to build here is using an envelope because amongst other reasons, works really well. Let's just take the front of an envelope, something like that, which we can now paste into our big diagram. So when we're sending data back and forth, we're actually sending, virtual envelopes back and forth. Now in our human world, an envelope needs a few things on the outside. So if I want to send a letter or a card to you, or just to anyone, what would I need on the outside to write on the back of an envelope? Imagine maybe it's slow right down and put it into simple terms. If I'm trying to send you a letter, what am I going to put on the front of an envelope? An address. Okay, so in terms of address space, what would we expect to find in address, like a physical address? Send and a receiver. Reza, that's actually the answer I was looking for. Exactly. So perhaps in the middle, I need to put some recipient's address, a sender, recipient, and also to return to sender as well, the address of me, some other implementation details too, which we'll go into. But what's something that I might put in the top left corner, or by convention, or the back of the envelope as well, is my own address. That's me as the sender in terms of getting it back to me if I need so too. So my own address, my own name, shall we say too. We might even put a little memo at the back there just to tell you 100 units in this case, or fragile, or some other convention, to tell us a little bit more detail about what's inside that envelope so that the postman or whoever's handling this can actually find out a bit more, conceptualize what's inside. So this metaphor works really well because it's actually pretty apt for what's going inside or underneath the hood here with computers. So when you have a computer plugged into a network or wirelessly over a network, it actually just really is sending these virtual envelopes back and forth, which at the end of the day are just patterns of ones and zeros, again, or binary data that represents your email address, okay? So your email or the request you're going from a web server or any nature thereof. So really what you're getting at the end of the day here, back from that web server, let's see if we can formalize exactly what those lower level primitives are, consider exactly what they're layered upon on top of each other, because we can therefore build thereafter almost anything we want on top of that infrastructure. Because once we understand what those lower level building blocks are, we can do almost anything online. So let's conceptualize how we can actually send that address in the first place. After all, when I turn my laptop on, when I put my phone on or my desktop on in the first place in the morning, how does my phone, how does my PC actually know its own address on the internet? How does it know where it is? Because just like you and I are in the real world, in the physical world, we need to be uniquely identifiable in the grand scheme of things in the physical world in order to even receive a package from Postman Pat, to receive a package for your birthday. So computers too also need to be uniquely identifiable on the internet. Right. Okay. So for our intents and purposes, we can even consider the internet to be an internetworked collection of computers via wireless or what done wirelessly too. There's some kind of interconnectivity amongst those devices too. And these days, all our phones, Internet of Things, and devices as well too. So let's just stipulate somehow that there's a physical connection or even a wireless connection between those devices online, between all those various devices. So we need some kind of address. And Rez is asking me for a DHCP server. And that's actually a good point. So let's put this into the analogy. Just like if I'm trying to find a real building in the real world, I would still need some kind of address, right? So if I ask you, for instance, who lives at 221B Baker Street? Does anyone know who lives at 221 Baker Street? As per Arthur Conan Doyle stories, Sherlock Holmes, Mr. Watson as well. They live there. Can I slow down? Yes, sorry. I've been told as well. I'm a fast. Yeah, so let me slow right down. So with that precise information limit, what I'm saying is, can I send a package or anything else through the letterbox, through the physical world, for it to arrive at Mr. Sherlock Holmes' letterbox? Yeah, well done. Yeah, I can. So, but what if instead, though, I wanted to send an email and get it to that building, or really just Sherlock's email address, wherever he's physically in the world, because right now he's somewhere else. He's on holiday. How can I do that on an internet working device like his phone in his pocket? So, what bits of information would I need to know to physically achieve this? To send an email to Mr. Sherlock's home when he's not at home? How would I get it to his pocket? So, I would need something else then. Not his physical address. I will need to know his phone's address, his IP address, or at least in the case of an email, the mail server which is responsible for sending and relaying that message from me to him. Well, it turns out like most networks these days, Rez has pointed out, have something called a DHCP server. DHCP server, or dynamic host control protocol. So configuration protocol, sorry. It was just another fancy way of saying that there is one server constantly online, which is listening out or looking out for new laptops or new desktops or new phones or new devices online, new devices to wake up and suddenly be turned on and shout out, well, the digital equivalent of saying, hello world, I'm here. What's my address? Okay. So the purpose in life of this DHCP service is to just answer that question, what's my address? Where am I? So to say, Mike, you're going to be address 1234 today. Najma, you're going to be 4567, and so on, or any number of possibilities to represent my uniquely identifiable address. So then DHCP servers are run on these run by system administrators in a company or in an internet service provider, an ISP, but more generally, they're run by whoever provides us with internet connectivity. It might be you. It might just exist on our network. It might just be pre-configured. But after all, those DHCP servers, they give us other bits of information too. After all, it's not just sufficient enough to know what my own address is, because how do I really know where everyone else is online? Well, it turns out that the internet is filled up with all kind of other devices. There's other things online which we're going to call a internet router, which you've probably got one at home underneath some curtains full of dust. So an internet router whose purpose in life really is just to, as the name suggests, route information from left to right, from point A to point B to point C, and so on and so forth. And those routers then, similarly, they need to know the address of other devices online. They need to know how to package on, how to pass on those virtual envelopes, so to speak, in which direction to send them on to. So those DHCP servers not just tell me what my address is, but also the address of the next hop, shall we say. Because me as my own little laptop, my own little desktop here, I have no idea where 99.999% of the computers in the world are, even higher actually than perhaps. I just have no idea where the next computer is. I have no idea where you are right now, but somehow I need to get to there. So I need to know where the next computer is on the internet, so that if I want to send information from this computer to you so that it leaves this room, then all the routers need to be configured by people who aren't me, system administrators who beyond these walls know how to route data from one place to another, how to get it from my computer to yours. And we can actually see evidence of this all the time. So generally speaking, you might be 1, 2, 3, or 30 different hops, so we say, or steps in between me and my destination, the email and that virtual envelope. And those routers are all configured by people who know how to route that data. So we can see this when we have evidence of this kind of underneath our fingertips the whole time. And if you've ever poked around, you might have seen traces or evidence of this around. Because if I ever want to see my own address, you keep an eye out a number like this, which looks a little bit like this. It's a number dot number dot number dot number dot like that. So any number of those placeholders represents a specific value, either starting at a 0 or ending in a 255. In other words, each of those hashes or lines can be any value between 0 and 255, and that range, 0 to 255, represents, well, 256 possible values. That's 8 bits, and what we know about 8 bits, well, ergo, any of those placeholders represents an IP address of 8 bits, so 8 plus 8 more plus IP. So an IP address, by definition, is how many bits? 8 plus 8 plus 8 plus 8, that's 32 bits, and there it is. So an IP address is a 32-bit monster like that. So IP is an acronym as well. You've probably heard of or seen before somehow. Even if you've not thought and hard about it, what it stands for, you can probably guess it stands for the Internet Protocol. So Internet Protocol just mandates that every computer online, at the risk of some oversimplification, just has a unique address called an IP address that gets from point A to point B. And those IP addresses look a little bit like what you see on screen, like that. So those IP addresses are composed of 32 bits, like that. So how many possible IPs are there? How many possible machines can we have on the internet? Does anyone know how many possible machines we can have online? 4 billion, Rezo. That's right. So 2 times 2 times 2, well, 2 to take the 30, 2 to the 32, that's 4.3 billion. Yeah, so near enough. We have 4.3 by design of the IP address space. We have 4.3, give or take, permutations of zeros and ones. So if you have 32 in total, that gives us 4.3 billion. That's IP version 6. That's not a good idea. Version 4, addresses and the like. Now, again, if this is a new module to you, it'll get explained to you thoroughly and slowly. But let me put it this way. Now, £4 billion, that's an awful lot of money. Trillions, yeah, a number which I can't even pronounce for IP version 6, but we're still, so omnipresent is IP version 4, which, I mean, 4 billion, 4.3 billion to be precise, is too much. I mean, 4 billion friends, that's a lot of friends. 4 billion hot dogs is a lot of hot dogs. We can all agree that 4 billion is a big number. It sounds big, but pardon me, each and every one of us probably carries some kind of IP address in our pocket, to be sure, in our phone, in our wrist, on our fridges nowadays, one or more computers in real life, then not to mention all the other devices that are servers in the world that also need IP addresses. It's actually not that much. Yeah, believe it or not. In fact, let me tell you in the chat right now, unidecillion IP version 6 addresses. That's the answer. So long story short, that's IP version 6, but IP version 4. IP version 6 is what Matty's just mentioned, is a ridiculous amount of number. Okay, it's decades old. This newcomer IP version 6. There isn't going to be a version 5. IP version 6 is only slowly gaining traction because we're running so short on IPs that it's becoming a company a problem for big companies, for organizations, and beyond. So we will eventually adopt IP version 6 that will use 128-bit numbers instead of 32, which gives us many, 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 many more permutations of that number. A number which I can't pronounce. Undecillion numbers. So that should cut it for a long, long time. But not every single computer online needs a public IP address. Only those envelopes, okay, so to speak, that need to leave my pockets or my home or my to get to point A to point B, as it turns out, as a short-term mechanism to squeeze out a little bit more utility out of those IP version 4 addresses, out of our 32-bit addresses, where it's still omnipresent and most popular amongst all the versions, we can actually distinguish between types or versions of IP addresses that go online to the internet, so to speak. And that's what we call between the public addressable space and the private IP addressable space. So indeed, if you've seen these before, a number like 172, well, any number of these here before it often happens lower. They start with letter 10 or 172 or 196 dot or 168 dot. Then that somehow, some way represents what we call an IP, a private IP address like that. And indeed, this is just a little feature of your router, probably in your home or the bigger router on your corporate network, that allows you to have an IP address that's only used within the company, only used within your home, and cannot, by definition, be routed publicly beyond your company, cannot go outside your walls, because the router simply will just stop it. And so what we actually have here is the beginnings of some kind of firewalling mechanism, if you will, some NACL, if you want to, because in the real world, like a firewall is designed to stop a fire from space to space. A virtual firewall, in this case, is going to stop ones and zeros traversing through walls. It prevents it from going from one place to another. So in this case, we already have a mechanism via public and private IP addresses to keep some of our data securely. Right, so with very high probability securely within our company versus allowing it to go out onto the public internet. So we'll see some of the, onto Rez's point about NATing as well, network address translation. We'll see some of actual computers from Mac OS and Windows alike. If I go over to mine right here, this will reveal to me the addressable space of where I am right now. And you can see this, by the way, on your own machine. If you travel over to, depending on what operating system you're on, if you travel to your Wi-Fi settings, you can search here for your internet. And indeed, I can see if you focus down here, a little bit arcane, I can see my IP version 6 address. If you make it out right there, now that's 192.168.0.23. There is a 1 in 256 chance that you and I had the exact same address right now. And because it starts with the 192.168, that tells me it's a private address, just like we see right there. It means it's private, and indeed, I'm talking to you from within my home network. And so that suggests then that it's used to route amongst computers in the world, but not beyond that as well. So then what we need then is some other, what I'm going to get to is some of the address translation to help me achieve that. If I go over as well to more advanced properties, I think here, I should be able to see, not there. Sometimes I hate that the fact they move this around. Where is it? Yeah, okay, so I know it's kind of small, but you can make out just about my default gateway or that's my default gateway. There we go. So my default gateway, which is 192.168.0.1, that's synonymous with my router, which is, as your internet gateway on the cloud. So if my default route says the default route is that first hop, the first thing that leaves my VPC in cloud terms. So if I want to send an email outside of my home network, I need to go and visit a web page. I need to do anything online. All I need to do is hand that virtual envelope. I need to go to my default gateway, my internet gateway, and actually send that web request off to my machine on the local network to wherever it has to go thereafter. And I have no idea where it's going to go thereafter. I really don't. That's the whole point of this. The whole, 2, 3 hops thereafter, it's clueless to me. But that's why we have the whole point of the internet and even more routers and out there. Because the routers, they intercommunicate with each other and they relay that data from hop to hop until it actually finally reaches your destination. So where did I get my IP version 4 address from? How does that work? Where did I get my default gateway from? So I got it from the DHCP server. That's what actually assigned that as its own, as me as 23, and the internet gateway, which if I type in here, if I talk to it directly, 192.168.0.1, which in my case was my default gateway, will appear to be in Portuguese because that's the language I've currently set up with. But you will see it in a similar configuration to your own. Depending on your internet service provider, it might be .1 or .254. Again, so this will be somewhat similar. If you travel over to Mac, it'll be the same thing, which is to say that when you're ready to send something off, you simply hand that envelope off over to that router, that device that's living in your house, and that particular router, its job ultimately is to become that first hop. And we talked about that hop, which is really just a border gateway or a border router, literally referring to a computer that's physically or metaphorically on the edge of a network of the company. So its purpose in life is simply to change what's on the envelope initially from the private IP address to a more publicly IP address, thereby maintaining this one-to-one mapping. So this might result in the world that everyone thinking that you and I and everyone actually in my house right now has the same IP address. But that's not actually true, because how do I distinguish my computer from my family's computer, from my phone, shall we say? Even though we have the same IP address, how does that mapping really work? So each of our personal devices, from my watch, my smartphone, my PlayStation, they all have an IP address. They also have a private IP address, because that router, my router, can actually translate something via network address translation, which is what Rez has pointed out, NAT, from a private address to a public address. That's what I'm going to call Nathaniel, or network translation. And so in a way too, can a company help mask the origin or the identity or whoever it is that is actually accessing some internet-based service? Now, of course, the same person could actually log in, that's leaving the company, and come back in, via some other mechanism. We could actually figure out who was accessing that server at that particular time. But, the outside world beyond the router would have no idea. They would need a lot of help actually figuring that out. And so that's done there by some reason in order to just use one public IP address amongst hundreds of thousands of people. So frankly, we just don't need to have that many IP addresses, therefore solving the shortage of IP version 4. So what might actually just be a technological motivation can also have those little side effects as well too. So IP address, Internet Protocol, let's talk about that. What does that actually mean? A number to identify computers on a network. Now, to be precise, it's a protocol. That doesn't mean it's a language per se. It's not a programming language. It's really just a set of conventions that govern how computers find each other, how they intercommunicate. So IP specifically, say if I want to send that message on the internet, I'm going to write the sender address on that envelope. I'm going to send the recipients on that envelope as well. I'm going to make sure that envelope knows how to get from place to place. So it's going to be able to know how to go back and forth with its appropriate directions. So IP gives us some other features too, which we'll see fragmentation amongst them as well. But it turns out for efficiency, if you've got a really big email or something, IP, whether it's a PowerPoint slide or something that you're trying to send back and forth, it's not really fair for everyone if you're trying to jam that onto the same network to the exclusion of other people's data at any given point in time, because you're actually fighting over the contention. You're actually fighting over the same bandwidth, so to speak. So fragmentation there is this idea of taking really big files into much, much smaller pieces and then send them into smaller envelopes that eventually will get reassembled at the other end. You will know that in S3 as a particular kind of technology known as multi-part uploading. So there is that compelling feature as well. Pardon me, I just need to turn the fan. I just bullets. It got very, very hot all of a sudden. So this, of course, leads to a very slippery slope of implications for net neutrality and other companies or governments who actually start to distinguish between the quality of service and this type of data too, another type of data. Because, I mean, why might they want to do that? Think about this. Well, it's a very quantized fragmentation. So this idea of, so fragmentation is to quantize this as a very small unit of measure. So within these packets, you've got additional information, not just addresses, but also some hints as to what might be in those packets. Like we saw on the sticker label, you might say fragile or something else there within. So, is it an email? Is it a web page? Is it a video conference? Is it Netflix? Is it Mrs. Lion? Is it some competitive service? Think about it from the point of view of the government who might be regulating those things in order for to maintain net neutrality. It's a dangerous path to walk on. So ISPs or companies or governments can actually distinguish amongst those different types of packets and treat them, at least theoretically, and also really these days, a bit differently. So really, they're just derived from those basic primitives. And now we can actually go very, very low level. If you want to look back at the formal definition that humans created some time ago for what IP address is, so we can see what looks like this. Chantal, that's exactly where I was going to go. Thank you for pointing that out. This is so. I just got a message from that. Right. So from this is kind of an artist rendition here. Let's get this one. Uh, 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 um, yeah, that's okay. So at the top here, we've got some numbers, okay, and these here they represent to some extent some unit of time. So 0 all the way to 30, well 31, but 32 spills over. So here's bit 0, bit 7, bit 15, 31, and the first such bits. So we start at 0, and you can count as high as 31. So that's our 32nd bit. So we can see a couple of details within this. Let me see if I can actually make that a bit bigger. There we go. Slightly bigger. Okay, so we can see things like for example, we said the source address. When I'm writing my envelope, I need to know where am I sending it to, and then of course that's the whole width of the picture here, 32 entire bits, indicating that it is a 32-bit value composing of the source address and the sender's address as well. The destination address, well, that's just as wide, so that's another 32 bits, and there's other options as well, like time to live. You can say just how many routers this can be handed off to before we just say, you know what, I don't know where this destination is. I'm going to give up. My time to live is I give up. There's other fields in there as well too. But what are we really looking at? This is just a diagram or an artist's rendition of what it means to send a pattern of bits of ones and zeros represented or stitched together. So those first couple of bits here, they refer to version. The next couple of bits refer to IH, so internet header length, terms, type of service, total length, and so on. So eventually the pattern of bits that represents a source address and the destination address. Now, any computer, your phone and likewise, that's receiving this series of bits wirelessly or over the wire in the form of wavelengths or light of electricity in the wire, it simply just needs to realize, oh, once I've received this many bits, once I've got to 32, I can infer where those bits, what represents my source code address. Oh, that's my destination address. Oh, I see. So again, this is very, very low level, but it's more pleasant to think about things as a letter, shall we say? So that envelope just has the information written on top of it, which we can think of as being like this, with address. So let's not worry too much about the abstraction below this one. Let's just when we get in the weeds of it, so to say, let's stay here at the kind of envelope level, because it turns out that IP address, well, IP is not the only protocol that drives the internet. In fact, there's several, but perhaps the most common one by far is one that you've heard of as well that commonly goes with IP. So Lembe, if point being that IP version 4 has been in short supply, sorry, the P6 or the IP version 6? Okay. Just to steer back the conversation a moment, when the distinction between IP version 6 and IP version 4 really was, I can't remember the name, DARPA or the company behind this. Who was the company? ICANN or IANA or ICANN. I can never remember which one it was. They're responsible for steering the ship and making sure that we have the appropriate they released what we call the NIST documents of 1918, RFC 1918 documents, and they reduced the fact that we have too few IP addresses and too many people. So long story short is we decided let's reserve some of them, and they're going to call themselves by class A, B, and C networks, largely depending on the size and the sheer power of the companies who are associated with them. So big companies like well, it's an American company like Ford's, the Department of Defense, MOD, so on and so forth. They were given big ranges like a 10 dot range, and that stayed exclusively within their own network. Now, you and I are we don't have that need, so we get associated with the 192.168 address. Just like I showed you a moment ago, when I look at my address, I can see quite clearly that I've got a 192.168 address, which is to say, thanks to network address translation, everything within my own network gets abstracted from you thanks to network address translation and hides it from me. So we can basically squeeze water out of stone and get far more IP addresses using the IP version 4 technique to accommodate the fact that we're overexerting the amount of people that use them or need them. So to facilitate this arrangement, we have something called network address translation, which is now being phased out slowly for something called IP version 6. And the reason you don't know about this is because IANA made that mistake a while ago, IP version 6. So IANA or ICANN, I can't actually remember who it was. They decided, well, let's roll out a new hexadecimal IP address space, which is going to eventually take over, but we're a long, long way from that too. The best case we can do is slowly roll in what we call dual networking. So we can have IP version 6 and IP version 4, but by nature of there being so many IP version 6 addresses, there's just no need to do private and public addressable space. That's a separate discussion, which I can reserve to one side. But certainly we can think of it as being IP version 4, because that's the one that you and I actually currently have. IP version 6 just hasn't globally been adopted nearly as much to the same extent. What is still true, though, with IP version 6, it does require something called TCP at the back of it too, which is another protocol you may or may not have heard of. Have you ever come across or heard of something called TCP? So the transmission control protocol. Yeah, okay. So we've got a couple of nods. Now, this is, again, another protocol. It's not a language, it's not a programming language. It's just a technique which solves a different problem to IP. So rather than just the simply of the focus of addressing computers on the internet and making sure that data gets from point A to point B, well, TCP is all about, amongst other things, guaranteeing delivery. It's what we call a connection-based protocol. Based protocol. It's about guaranteeing delivery between places, okay? So TCP adds additional zeros and ones to that envelope on the outside of it to help us get to the envelope to its destination with much, much higher probability, as opposed to UDP, which I would take you a joke about, but you might not get it. Haha. All right, so in other words, the internet's a very, very, very busy place. So servers are constantly getting more and more users. Routers are getting any number of more packets at any given point. So sometimes there are spikes in connectivity too. So people might be turning to some news broadcasts. We might be all going to the same, Teams Zoom meeting right now, or just downloading the latest news all at once, or everyone's playing the same game at once. There's something happening in spikes, okay? And so there can be these bursts of activity, which you may think of in terms of scaling activity, okay? And honestly, we humans, we don't necessarily engineer things with burst of activities in mind, because that's an exception to the rule, right? So routers can get very, very busy. Computers can get busy as well, but that happens rather sporadically. So, and when things do get busy, they might actually receive an envelope or information and realize, oh, wait a minute, I don't have enough hands to have all this extra information. And packets, well, what happens to packets is, sorry, just thought I ripped out my envelope. So when we get very, very busy, our envelope gets dropped, In fact, that's a term of ours. That's right, to drop a packet. Have you ever heard of dropping a packet in TCP? The reason it's called a yeah. So all packet, yeah, okay. So that's a term, to drop a packet. It means just to ignore it, shall we say. So you don't have enough memory, you don't have enough RAM inside your computer, enough your system to hang on to it for any length of time. So you just ignore it, right? That's what you do. Now, this would be pretty frustrating if I tried to send an email to you with only some probability that it actually goes through. Think about that, In practice, it feels like it happens sometimes, but in reality, it's just going to spam. You do actually want emails that are being sent to actually be received. Otherwise, the world would just be a nightmare. So TCP, so when I request a web page, for example, as opposed to Reza pointed out, there's another one called UDP, where it's a best effort approach. Similar in spirit to maybe SQS when you've got FIFO versus standard queues. In practice, it means when I try to go online, when I try to retrieve information from online, when I go to a website such as this one, I try to get the full web page, right? There's no point in me getting only part of it. So yeah, therefore, what happens is this gets chopped up into little teeny tiny fragments. I don't really want to just receive a part of it. I actually want to receive all of the fragments. So fragmentation is taking big chunks of data into smaller ones, and then not only just some paragraphs of an email, but actually the whole email. I don't want to receive sections of a web page. Give me everything or nothing. So TCP then, by some nature, like we say, so TCP, at the end of the day, just make sure that, well, not at the end of the day, hopefully, but ultimately I get my data. So what TCP does is it actually just adds a little bit of a mental note, shall we say, that this is packet number 1, and this is packet number 2, and this is packet number 3, and so forth, and bigger and bigger in the case of a bigger file there. So what TCP does is when the recipient, when someone who gets the envelope back of the rep request of the email, they realize, okay, well, I've got an address, let's check it. I've got numbers 1, I've got numbers 2, I've got numbers 3, I'm missing number 4. So how do we go and retrace that? Okay, so if I realize I'm missing a portion or a part of my my packets, well, that's a problem. TCP goes and tells the computer, hey, you know what? Go and send that message back again to the sender saying, hey, I got everything except packet number 3. I missed a little part of what you were saying. Can you please send it back again? Please resend it, essentially. So that's going to take a little bit of time, because the point is we're trying to retrace our steps and make sure we've got everything we need to. We can't miss any part of information, which is in adverse effect to UDP, which can step aside that issue, which just says best effort ordering. So by that nature, it does present itself as TCP. It takes a little bit more time. We go through this handshake mechanism, but that packet, it will be resent, and TCP, by nature of it being a protocol, will know how to reassemble that in the correct order so that you, the human, the web server, can ultimately see the entire thing. You know, you get the entire web page back, not just some portion of it. So what does TCP really look like? So let's have a look. If we take a look at the quick peek under the hood here, we see something nature again. So, and two, do we see a very similar pattern of bits? Notice as well, 32. That again is handled by IP address. But you see the mention of this now, something called a source port and a destination port, much like in terms of nautical terms and shipping terms, when you go to a port of a harbor. Forgot the word. So this is what we call the porting, and we've also got sequencing or sequence number underneath that too. That helps a lot with delivery as well. It's making sure that it's in the right sequence number. Okay, when I said if you miss out one of the sequence numbers, you know whether to come back or not. There are other options as well down the page, which also relates to somehow the delivery of that information. Now, if we look up here, there are two parts. We've got 16 parts each. We've got so source port and destination port right there. Okay. Now, those two have, because TCP also does something else, it doesn't just guarantee that data gets from point A to point B, it also helps distinguish one type of data from another one. And in turn, which allows companies and other internet service providers or governments to really distinguish the different types of data that there is outside of the envelope. Okay, so in particular, what TCP does is again, it's a protocol, the transmission control protocol is used to convey this packet of information from one computer to say another. In other words, the point is that there's loads and loads of internet service nowadays. Okay, I'm sure in front of you right now you've got Zoom, you've got, I mean, how many millions of things do I have down here? All daemons running in the background. There's email, there's chat, there's video conferencing, there's games, there's God knows what else. There's web browsers, which are very power hungry as well, and a lot more. So there's a lot of possibilities, if that makes sense. A lot of things that can be running in the background. Lots of patterns, lots of ones, lots of zeros that can be inside of those TCP envelopes. Now, how then does a computer, when it receives the envelope, how does it know what information is inside of it? You know, especially a big company, how does it know when it receives a TCP envelope what's inside? So say Google, for example. Google is a big company. It supports all kind of services. To name a few, could you name me a few Google services? So what are products, what are services that Google offers? There's a lot of them. So much, in fact, that Google even has its own website called Killed by Google, because they go ahead and are the death of so many little startups. Killed by Google, which is annoying because I am a Google fan. I use VPN Go, I use Jamboard, I used to use Podcast, I used to use a lot of these things. I use domains to some extent as well. I even have it a Pixel as well. And they kill them. It just falls out the cycle and then developers start working on them. Yeah, don't develop on Google because you'll get killed. Right, so Google Maps, Google Drive, thank you. So those are the things that we can, all related to the Google ecosystem. So therefore, on that point, how does Google know what packets of information it's receiving? So when it's receiving a packet of information, how does Google know that that's an email sent by you, as opposed to, say, a chat message sent by you on Hangouts? Who remembers Hangouts? Who remembers Google Plus? All those things, as opposed to, say, a video received by you on YouTube or so on. You know, how does it know? Well, in other words, what we need to do is distinguish the services. Okay, Rez, that's it. So we need to be able to distinguish these services, what we see online, because at the end of the day, they're all just patterns of bits. You're on the right lines. That's the answer. So if we reserve some of those bits, or should we say markings on the envelope, for one number or two numbers or three numbers, in the case of some ports, we can really distinguish those ports rather easily. So in fact, HTTP is one of them. I think it's one that it's an acronym that you may not know what it means. If you're relatively if you haven't played around with it, that's fine, but you will have used it. I guarantee you will have. It stands for Hypertext Transfer Protocol, and it's the conventions by which web browsers and servers Right, port 80 is able to send web pages back and forth on exactly those particular numbers. So let's see how that works. By convention, humans decided some time ago that we need to give those ports a number, okay? So like you pointed out, Reza, exactly, port 80 was the one that just happened to be reserved for HTTP, for service number 80. So TCP port 80, does that make sense? TCP 80, that's how I know that I'm talking to a web browser. Right. And then there's a secure version upon that too. So 443, which you just mentioned as well. They decided to name that too, just because they'd already used a couple of numbers from 80 to 443 in between those values. They just got clogged up. There's other ones too. We've got IMAP as well. So IMAP is a protocol for emails by which you send or check your email. That's used again for different ports, whether you're using that in two ways. You can use that securely or insecurely. So that's 143 or the other one starts with a 9. I forgot the other one. The secure, the unencrypted version. You got what was it? 993. So 143, 993. Again, just encrypted, unencrypted. Same goes for SMTP, which again is for outbound email. SMTP, which again, if you think about it, is similarly 25, 200, and whatever it is. There's different kind of ports for these. Again, what I'm saying is that these, if they're familiar, they have been standardized, which is to say that some people, some smart boffins got together around a round table and said, that number is going to be for this particular service, for that product. Same goes for SSH. For my developers out there, what service might we use? 22, straight in, Reza, you're on it today. So say if I'm on a computer or a laptop, I'm trying to connect to a remote server, it tends to use something called port 22. And there's hundreds, actually, there's thousands, as many as 65,000 combinations of ports out there in the real world. But actually, only some of them are standardized, if that makes sense. So, which is to say that ultimately, only a handful of them should be memorized. The ones we just mentioned, 8443, 22, are probably the three main ones to actually recognize. But ultimately, I don't know why this is not working. What's going to go on the outside of my envelope is not just someone else's address, but when I'm a computer, say I'm trying to send one message to another person, do I go and say, you know, I'm trying to send some other thing to you, for instance, I'll write that in the top left corner of the envelope. I'll say, so I tried to get to you, which I'm going to say is 1, 2, 3, 4. Come on, pen. So, so I'm going to say 5. Oh, why is it not working? 5. It's not going to work because it's not being fair to me today. Why is that script not working? That's really strange. That's really bizarre. Okay, well, if you imagine right here, is we'll see a couple of numbers which relate to what we're trying to send to. So in the top left corner here, I'm going to say 5678, which is the recipient of the envelope. So who am I sending it to? I'm sending it to Mrs. Jane H. Doe at this particular address right there. Now, in the middle of the envelope, I can further specify and say, Mrs. Rebecca, well, no, sorry, the other way around. So I'm sending it to this person on behalf. So I am Mrs. Jane Doe, and I belong here. Now, then I would actually say something else like port 80 or port 443 or something else, which is to say I'm distinguishing for a web page. I'm distinguishing for an SSH connection or something else too. So rather conveniently, I would do, if only my pen was working. Annoyingly, it isn't. Let me see if I can get one. I think this is one that doesn't actually say with TCP IP. Right. Yeah, kill it and open it again. That's just going to take a while. Just like my face on screen. Got too many things on. Well, the point being that we can basically distinguish service with a port, and well done for those that got that. So it's of course because TCP's, I need to number these things too. It's a big request, it's a big response. So I need maybe 1 of 2 or 2 of 3, or I need to say how many packets or segments I'm about to send on the internet. So that way I can maintain a connection-oriented protocol using TCP like that. So ultimately I'm left with something that looks a little bit like that, that says, I'm going to that one. Let's go back here. Let's just do it this way. So I'm going to go send receiver. I'm going to say, I'm going to talk over port 80, and I'm going to say that's 1 of maybe 4 envelopes. Okay, so that's me. That's where I'm going to, and that's my my any packet. You know, so that's my flanks, shall we say? And I'm also saying my segmentation details too. So on the outside, I've got all the things that I need. That way, I'm basically telling the relevant people what it is without you peeking inside. Hopefully, it's going to be received. So then TCP allows the recipient or someone who's going to look at the envelope and just realize, oh, okay, so you're talking to port 80. Well, I know what that is. That's my web server. Come right in. You know, Google can hand it off to the appropriate piece of software that governs the web service, the HTTP web server or something, so that it's not confused with something else like an email server or a SSH connection, a chat message, a voice call, a video, or so on. So, and these features drive quite simply from the fact that patterns of bits that esoterically happen to be laid out in such a way. But if we abstract away from that and stipulate just, if we think about it in the real world like an envelope, it's really just numeric values that somehow help us to get from one point to another. And that's really is, in a nutshell, TCP IP. Collectively now, those two protocols, TCP IP, which often so go hand in hand, are generally abbreviated as TCP IP. Again, they're two separate protocols, two separate conventions used in conjunction together to get to point A to point B. And some of this information might be written in different places, if you will, on the envelope, but largely TCP/IP settings are what you might look for on your computer to actually configure that level of detail. But of course, I've taken some liberties here. If my goal is to get from a message from my computer to another computer, a chat message, perhaps an email or something else, you know what? I'm pretty sure that I have no idea what the IP address is of who I'm trying to get to. So going back to an earlier question is, what is an IP address? I still have no idea of what the IP address is of Google or of Facebook or Mr. Lion or any number of other websites out there that I visit on the daily. In fact, do any of you actually know what phone numbers are anymore? When was the last time any of you learned a phone number? That's another matter, okay? So some time ago now too. So in the context of words, though, that's what we use together. But actually on the internet, we don't use words. We don't type numbers. We actually type in words when we're trying to get places, right? So when we want to reach some destination in the URL bar of your web browser, you don't type in 192.so-and-so or something else or something to say, yeah. So, right, so the IP address is that layer, it's the layer 4 protocol by which you have the map. So the MAC address is what's uniquely going to identify any address, whether it's a phone, a watch, anything at all. You're right. IP address is just that digital representation, which can be changed, it can be dynamic at the level above that in order to basically represent that digitally. But pretty much the same functions are filled by which you're trying to uniquely identify something, whether that's uniquely within your own private address space or publicly thereof. So MAC addresses and thereof, they're just other layers of the OSI model. So DNS, as mentioned, is how we get from facebook.com to gmail.com to lionhub.com to bing.com to any place like that. Because there are many, many domain names, so to speak, when we try to go places. So let's talk about domain names real quick. So, right, when I try to go online, of course, that's what I'm going to write on the outside of an envelope. So you and me on the human world, when I try to get to www.example or tinydancinghorse.com, we would like to do that in ideally as many words as possible, in letters, but words. So numbers alone are just not going to cut it because obviously reasons are bad marketing, bad remembering, bad everything. So if the IP address fixed to your laptop, meaning if your laptop breaks, what happens to the IP address? It will, so if the DHCP server is configured rightly, it should be able to be, so the configure of the DHCP server is what's responsible on your home network for giving out or handing out IP addresses. If your device is taken out of action, the MAC address will still remain. Every time you leave and come back, it actually might, there's a chance you might be assigned a different name. So say, for example, your home network, if you're like me, if you have a 192 network, you have a total of 256 devices. Now, what happens if you have 260 friends? What if you have 200, what if you have more friends that come to your house asking for your Wi-Fi password? Well, what's going to happen is you don't have enough to accommodate all that future growth. Therefore, you need to kick out some of the early addresses. And that's what the DHCP server is responsible to do. By some nature of DHCP, it will reassign those IP addresses to your laptop. So if you lose your device, well, that one eventually will be forgotten by Time to Live or some other nature, so that it's given or accommodated for newer laptops. Yeah, so DHCP will just accommodate growth, but we don't have the same concept online. We have something else called DNS online. And DNS, in similar spirit, is a way of mapping one thing to another. But in this case, DNS works by mapping an IP address to a domain or a name, a human-sounding name. Just like a phone book works, where you put your friend's name in, but you say, "What's your name?" I say, "Oh, it's my name. It's my phone number," and then you forget the phone number forever because you know that person's name now. Your computer, your contacts book, is responsible for keeping that one-to-one mapping alive. So it turns out, by similar spirits, a computer is going to similarly express what we humans know, which is those domain names, which is what sticks in our head. Go compare the market.com, that annoying marketing brand that stays in the back of your mind. Well, it works effectively far more than it would do if they just gave you a number, 0800 00 so and so. So as it turns out, we need the help of at least one more service amongst all these internet technologies. And that's what we call DNS, or the domain name system. Yeah. So so DNS, which is a big theme, it's just really just a server that come on. It's always going back to English. Yeah. So it's going to translate what we say, human names like gmail.com or sharepoint.com, whatever it is, bing.com, to their corresponding IP address in the back. So we as the humans, we have actually no idea where these things actually are hosted. Where are they situated? We have no clue. But odds are, that there's a human, there's a person in the world who probably works for these companies, works for companies like Cloudflare, works for companies like Google and other big DNS servers, right? Now, they know, and they've provided that he or she configures the DNS service to know that association of the domain names to the IP addresses. It's the equivalent of just some big Excel file with one column with names on one side and IP addresses on the other. Then we can answer questions from my server, from my computer. And indeed then, so when my phone knows what to do nowadays is when me as the human, I try to go to gmail.com and I hit enter. Well, the very first thing that my computer does is go and checks. It will check the recursor, so it might actually go and check the my browser, my operating system, and the likes. Has it been cached? And then it asks, if it doesn't know, my local DNS server. Where the hell are you? I had it here. So my DNS server, which is going to be, there we go. Yeah, there we go. So right there, I've got my local DNS server. That's right, the pig spirit. Yes, I'll have the same. Oh, will I have the same IP address, provided it hasn't been piggybacked and taken over? So Matty, if enough connections are made, if enough people come onto your network and sort of piggyback onto that space, then you could essentially get bumped out. But assuming that it will do a best effort order to retain and keep you statically. You can keep static IP addresses like your printers, like your stuff, while I'm off. So if I'm off if I'm not using it for a long time, I mean, a couple of months, say, yeah. But again, that's it, provided that your network router is quite busy and you have people on it. Again, if you're very popular, if you have a lot of friends coming home and they're all asking for your IP address, chances are you might get kicked out. But say if your old phone that hasn't been active for some time, it might inadvertently kick someone else off if you come back on after some time. To be honest, that's something I'm not too sure. How does it work? How does it kick people off after a while? Never start to think about that. DHC people, DHCP, reassignments. Oh, I hate things like that. Seems like the best thing I can find is threads or forums. Oh, so lease times, that's what I'm thinking of. 10 days. So if I leave my computer off for 2 weeks, I have an IP address of this and that. Will the DHCP server reserve that IP address so long as no other client in my subnet requests an IP? Then yes, it's possible for it to be reassigned. That is how it works. But again, I don't know how, it again depends on how long you've configured it to be, how long the lease time is. Yeah, or refresh interval. Depends how your route is actually set up at home, how your internet service provider works. But you can change the lease settings. To be honest, that's something that will, I mean, why would you? Why would you do those kind of things? The point is trying to automate that for you. Online though, it works slightly differently, which is to say that when you do DNS, Let me explain how that works. So DNS, as it suggests, is a way for me to get my domain mapped to an actual, find it in English, please. Just want to have an image or something nearby. I mean, yeah, that's the one I want. Exactly right. That's the image I've seen before. So when I type in example.com, the very first thing I do is press enter. My browser, my operating system, my computer, in turn, my Windows is going to go and check my local DNS resolver. It's going to have a conversion of whatever I typed in, example.com, to the corresponding IP address. It checks, does it exist? Has it been cached? And hopefully within my own network, be it my home network or work or something, it has the answer to that question. It saves me going through the additional rigmarole of checking out these other name servers there. But the world's a big place, right? Odds are that my little home server here doesn't know the IP address of every server on the internet. That just wouldn't make sense. Odds are that my server doesn't know the IP address of you. It doesn't know the IP address of your neighbors, because things are constantly changing within the network and outside of it too, as new sites are coming offline and not online all the time. So how do we know that? Well, DNS is basically this whole system, this whole hierarchy, whereby we have a very small DNS server, rather so to speak here conceptually, here on premise. But then we have this larger internet service provider, whereby we might have a small DNS server, Orange, EE, BT, so on and so forth. They probably have much bigger DNS solvers on site. So in their own data centers, in their own internet service providers, with much more memory, much more RAM, much more power, with a much longer list of domain names as well. And those IP addresses as well. But that's assuming best case scenario, they have them. And you know what? Even if they don't, it doesn't matter, because that's what they're going to call root servers. And at the root servers, similar in spirit to actual tree, is where everything starts. Okay, so in short, we don't always have the answer, okay? So what we're saying is, I don't always know where to get to point A to point B. Now, DNS is really just a simple case of a hierarchy. It's a way for me to go and check the IP address of where I'm trying to go to. Like, we know everything online nowadays has an IP address. It needs to be uniquely identifiable online because of the reasons we mentioned earlier. And so via DNS, rather cleverly, we're able to disambiguate the domain name and from the actual IP address. It's a hierarchy, this thing. It's also very recursive as well in nature. So if you look at this picture here, you start here. So your internet service provider is going to go and check, does it have the answer? Does it resolve that, first of all, for you? If it doesn't, they'll pass it on to a DNS root name server or a root name server. So like that, like an actual tree, that's where it starts, okay? So as per the name, the roots, everything is going to begin at the roots. So you can actually find out from the root name servers on the internet, the mapping effectively between all the .coms and the IP addresses happens there. All the .govs, all the .nets, all the .lions and stuff, all their IP addresses. And frankly, even if they don't know the answer, by definition of it being the root server, they'll be configured to know someone else. They'll have a friend who will know on their behalf. So yes, it's a hierarchy. It's also very recursive because it will pass on to the next person. So you'll ask your local server, which might even ask a more remote server. They'll be, who, if they don't know, they might ask even a further away server. And that server is going to say, you know what? I don't know. I checked. I don't have it, but I know that this server over there knows, so I can pass you onto that one. But eventually going through this back and forth motion until you get to the one server who bubbles it back the answer to you. Eventually, they're going to find out the server, the name for you. So it says web server, for example.com is hosted on 192.0.2, etc., which we then can supply back to you as a result. So yeah, explain better like that. Whoops, just got some noise. No worries. Yeah. Yeah, just gonna pop you on mute there. So what we're saying is that as an image. I'm just gonna post it there because it's kind of big. So can I send images on Zoom? Yes, I can. Okay. Well, long story short, what we can do is be very, very efficient. So we don't have to constantly go and check the same question. What's an IP address? What's an IP address? Because what we can do is cache those results locally. And so what is caching? Caching generally means just remembering, okay? Keeping some past answer around for longer. So if I'm going to be asking the same question again and again and again, my computer, my operating system can restore this in cache, so to speak, so that it's ready to retrieve that the second or subsequent queries later. So why bog yourself down on extra unnecessary overhead if you just store the information later, if you remember the past answer? Now, that does go without, being said. There are some downsides to this as well. Because what we're doing, we're remembering the mapping of a domain name to an IP address. Okay, so we've got an IP address, we've got a mapping of a domain name. They go hand in hand. Yes, I can save myself the trouble of asking the same IP address again and again, multiple times a day, per minute or something. But what happens if that changes? What happens if we have a poisoning attack or something of that nature? So DNS is the process of temporarily storing DNS records within any of those things too. I can save myself the trouble of having to ask the same question multiple times in a day, in a moment, if I can just keep it nearby. That answer, that past answer, stored somehow in a browser and device and a network. Yes. The catch, though, it's again, seems to be a trade-off here, is that if Google changes something, if Akamai changes something, if Cloud NS changed something, if I try to visit that web server and I've reconfigured something on their IP address level changes, well, it might actually be a bad thing. We might actually reach what we call a dead end in that case too. Time to live is precisely there for that reason. So that's by some nature of a time-based mechanism, some lease or some forcible expiration, DNS flushing as they say, we can actually reset ourselves back to normal and reset ourselves to ask our IP address resolver to go and fetch that information again for subsequent requests. Because we can save our time by catching, but that's if it's the right answer. Otherwise, we lose time. We can save time by caching, at the risk of correctness, if that makes sense. Because now the server's recollection of those IP addresses, it can become outdated. So this, there's a whole can of worms, really. Which is, so to speak, what it really means to be a network engineer in the world of IT is actually to go and think about these things and ultimately to solve some of those problems, how to get ahead of the game, so to speak. So yeah, there is no surefire solution other than just to expect that. Sorry, I just thought I heard my doorbell. I think I heard my doorbell. I'm not sure. I'm going to hope it wasn't me. Anyway, so we just have to accommodate those changes over time. So in Windows, yeah, can I see that solution myself? Well, if I pop open my same Wi-Fi properties as before, if I have a look at wide properties, it has changed now from Windows 11. It's kind of annoying, but you should be able to see not only your IP version 4 address, which is there, right there. But also I want to ask it, where is my local DNS server? And then you can see right there, my local DNS servers have been redundantly stored. Okay, so I've got not one, but two. So it was there all the time. Okay, my IP version 4 DNS servers have to be multiple, which is to say that if my PC, my laptop, and my browser needs to know an answer to a question, what is gmail.com's IP address? Where am I going? It's simply going to ask that local server, that DNS server, for that address. Does it have that address, that 182.213, so on and so forth? And that local IP version 4 DNS server, and this is important, okay, it itself cannot have a name. It has to be an IP address, because think about that for a second. It has to have an IP address. We need to know what the IP address of the DNS server is. Otherwise, of course, we get into this endless loop, because if we only know the IP address of our DNS server, but only the DNS server knows how to convert that to an IP address, then we're never actually going to be able to answer that question, are we? It's more like a catch-22, that situation. So, and even if it does actually have a name, well, we need to know that name manually, and it kind of defeats the whole point of DNS. So via DHCP server, somehow, it'll actually have to know what its IP address really is. And here I can happen to have redundancy, like most of us, probably you have as well. You've got two IP version 4 DNS servers. Okay, I don't just have one, I have two, just for redundancy. And again, I automatically got those just when I turn my PC, my phone, they automatically know via that local DHCP server where to find those local and next step DNS resolvers. So let's see if we can mimic this in terms of PC hardware. Your phone does this all day long, okay? Every single time you go online, this happens rather unbeknownst to us, but it happens every single time. I have here what we call a terminal window, which for some reason I forgot what it is. Let's just make another one. There we go. So this is just a textual interface to my computer here. It exists on, you've got them on Mac, you've got them on Windows, you've got them on Linux, you've got them other operating systems as well. I'll show you what I mean. I was trying to get it on here, but it just took me through the whole installation process, which is rather annoying. Because I had one this morning and now it's just kind of... Where's my party? Ooh. Yeah, so terminal. Okay, so yeah, sorry, I was just checking what we. So this is the command line interface for the CLI, which I do really recommend you get a little bit more comfortable with. You will resist it for as long as possible, but eventually you will need to learn a little bit about this. It's just a textual interface for your computer. It's just a quick way to get to place to place. It exists on all computers, so why not? And what that does really just allows me to execute textually, programmatically on my keyboard here without any mouse to exactly the same kind of commands that I would do with your browser, your software, or effectively whatever else I'm doing that's running on my behalf, okay? But I'm just doing so programmatically via a command line interface or a shell, which is, again, interpreting my actions. For instance, I genuinely want to know, what is the IP address of gmail.com? I can ask it like follows, just say nslookup or nameserver lookup gmail.com. And with any luck, it should be able to tell me right away, nslookup for nameserver lookup. I can see it and I go ahead. Can anyone tell me what is the nameserver? Oh, I should be changing to black and white. Oh, I don't have to do that. But yeah, I've gone for purpley theme because of Ubuntu. But I can tell right away from there just what my IP address server is, which is 142.250. See if I can make this bigger. How do I do that? There we go. Slightly better. So from this alone, I can see the IP address of gmail.com lives there. I knew I'm trying to get to gmail.com. It's returned to me the address 142.250. DNS. Makes sense, right? I can actually literally type in gmail.com, name server lookup of anywhere else. Another example, please. Google. Well, Google might be a bit, let's try to do google.com. Why not? So, yeah, okay. So it's going to that one right there. So, all right there. Facebook.com, the same idea. You're going to get a different IP address, a public IP address for any suggestions you may give me. So Facebook.com. Now, this is a little bit interesting because here visually I see on screen, Facebook.up.com. I was thinking about up in the keyboard. I can't talk and type at the same time. You know what I mean? Similar network subnets. Yeah, on a perfectly different but reasonable part of the other portion of the network, you have 192.54.250 and so on. So this is coming from my particular server right there, which is 172.0.0.53. Again, that's remained constant. But what's really interesting is I'm pretty sure, Google is a big company. Everyone knows Google. And therefore, I'm pretty sure they have more than just one IP address. Yeah. Seems a bit illogical to just have one IP address for Facebook.com or big FAANG companies like that. Well, it turns out that there is a big IP, like Divesh has mentioned, there are multiple IPs that can be assigned to the same domain. So let's imagine that they have not just one server, and therefore not just one IP address. Does that make sense? So they have not one server, but multiple servers behind which there are multiple IP addresses. You might see where this is going. And you might, well, it turns out that there's a whole hierarchy of servers out there, most likely that my data goes to. And thereafter, when it goes to Google's end, it gets dissipated and so on and so forth. But the one IP address that they're telling me is theirs right now is, well, if Facebook's telling me right there is theirs, is this one right there. I wouldn't say this is, well, this is technically a scripting language, but it's one called, I'm currently using Bash. There are other alternatives out there. This is Bash, Born Again Shell, but there are others. So we've got Esh, which is just SH for shell. You've got SZSH. You've got others which are more scientific. You've got ones which are good for floating point numbers. But honestly, that's a discussion point that doesn't matter because the one that's defaultly installed on most Debian-based systems, like Ubuntu, like Fedora, like Red Hat, including Linux version 2, is Bash, which is BASH. So minor differences work very, very similarly. Give or take, minus profiles and all that stuff. I'm teaching Linux at the moment. Oh, okay. Whoopsie daisy. Anyway, so so if you're interested in finding out more, I suggest you go and read shell bash, which is again those commands we've seen before when we type in bin bash. You've seen those other user data scripts. Again, that's talking the bash language. Yeah, bash, which is actually telling you in the binary, which is where Linux stores its executable files. It's meant to find, or the compiler should interpret this by knowing where to search for in the Linux file hierarchy in the bash configuration. So that is a directory in Linux wherein it stores all the configuration profile settings for you inside of that file system hierarchy. So after that, the compiler knows what to look for, essentially. It's got all that pre-configured bash. The CLI will know what to look for inside of that file system hierarchy. The forward slashes, again, it's no different than just saying another folder within a folder within a folder. And that's a message you're talking straight to the compiler, which in my case is this terminal window right there. But that's neither here or there, okay? Because what I'm doing is pretty much the same thing I can do on anything. If you're any on some kind of Unix-based system, if you've got a MacBook at home, then it's going to be the same thing. In fact, the forward slashes work the same with Mac, which is a forward slash. Now, annoyingly, Windows users do this. We're a bit hipster like that. We have to do things some other way. And you'll notice it goes backwards, doesn't it? It goes like, so now notice how on Windows, it goes the other way around. They just had to be different, didn't they? Anyway, so what I'm doing is I'm sending a packet of information here, asking for a name server lookup of facebook.com. I'm going to find on their end what is their name server. But once my packet of information has gone there to Silicon Valley, Mountain View, California, wherever it is, wherever their servers tend to be in the world, then they might have any number of servers, dozens, hundreds, thousands, depending on how many they have, that can actually receive my packets. So in terms of Amazon, well, we know them as being a regional service they've got all over the world. Linux dominates about 90% of servers online, which is why I'm suggesting you learn it, because it's an invaluable part of being an architect and an engineer. You're going to bump into it in some shape or form. You don't have to be an expert. You don't have to be maneuvering in and out, but you can be at least comfortable with, the low-level primitives of shell scripting, which is getting around and understanding the file system hierarchy. Again, it just happens to be the one that's most in use because, well, did anyone see the article 2 weeks ago about Germany using Linux? Anyone catch that? Yeah. So Schleswig-Holstein, one of Germany's 16 states, on Wednesday confirmed plans to move tens of thousands of systems from Windows to Linux. Yeah, they're moving away from Linux. They tried again back in the early 2000s in the noughties, but so staff weren't trained well enough, or LibreOffice, which is some, I don't want to say knockoff, but it's an interpretation of Microsoft Suite. It just wasn't nearly as fleshed out as it is today. And you and me and pretty much your grandma can just get online and understand. If they can understand one computer, they can understand another one, right? So they can understand after some getting used to, well, Firefox or Mozilla's Firefox. Again, Mozilla's just kind of spun off into this other separate mail server company, but it still remains as the default choice, Mozilla Firefox as the default web browser of choice. You've got other things like Boombox or Rhythmbox, rather for media, Thunderbird email for email. Again, it will vary from Debian to distribution. But again, it's SaaS. Yeah, exactly right. And by the way, this is what we call a head mount. What we learn about it when we term EC2s, when we look at EC2s, they're headless because we work programmatically remotely via SSH. So we don't need all this fancy firmware, all this stuff that's kind of churning up behind the scenes and processing a lot of this GUI. It's what we call GNOME-based, GNOME 3 to be precise, which is just, again, the graphical user interface that we see in screen right now. People like it, people hate it. It was kind of cut the community back in half in 2011, but it remains. I think it's somehow designed to mimic that of a phone. It's got that kind of touch sensitivity when it's got scrolling windows, because again, Linux gets used on 90% of servers, including things like tablets, IoTs, microcontrollers, so on and so forth. So it does accommodate to the general public. I've seen leaks of Windows 12, and it's kind of going down a similar path, by the way. So next year, there's been a concept art being released, and I don't know if I like it. I really don't think I like it. I'm still disliking Windows 11. I'm going to dislike Windows 12 even more. I'm genuinely considering getting a Mac as well. Anyway, so back to the point. So getting data from point A to point B, because once it's in Google's end or Amazon's end or whoever I'm going to talk to, that's theirs. Okay, they've got many servers that they have. It just happens to be the outward-facing IP that your phone, your Mac, or whatever it is, your phone actually uses. So let's see if we can trace this back to Mountain View, California. Let's go back to my thingy-majig. to my terminal. Let's clear that. And I'm gonna. So what I'm gonna do is I'm gonna go ahead and quite simply say, let's trace the steps. Let's Hansel and Gretel our way back to California. Okay. Zoom out. So annoying. Oh, I don't want to do that because I want to come back. Q for quits. No, exit for quits. Exit. It was exit. It's either Q or quit, or Q or exit. It's one of the two. Terminal. I'm just here promoting with Linux. I'm like, how do I do the basic things? How do I find the terminal? I'm a complete monkey. Terminal. Okay, so let's see if I can trace the packets. So for me to get from my computer via the CLI, via the command, literally a thing called let's trace the routes. Let's trace routes. Let's see the packets of information travel from my computer, leaving my computer, and make their way ultimately back to Google. So trace routes, trace, yeah, google.com. What? I thought it was that one. Ah, okay. Yep. Sorry, that was the Windows command for what was it for? Reverse DNS lookup, right? Yeah. So okay, same idea, but just sticking for the Linux for the Windows machine. Same principle. But what we're saying basically is we've gone ahead and answered that by quite simply saying, go and fetch me how many hops for me to get to Google, how many hops to go to Facebook, how many hops to go to wherever I want to go. So I'm going to see here, line by line, the sequence of IP addresses of every single router, which is to say that every single hop between myself and my destination server at gmail.com, at google.com. So on occasion, though, we're going to see these little things here, these asterisks, which indicates that that router is basically not having any of this. It says, get out of here. I'm not going to respond to, I don't respect your requests. So I can't see any IP. I can't see any information about that, basically. But what I can see eventually is a series or a total of 30 hops or 30 steps, shall we say, that leaves from my PC and ultimately ends up at google.com. And along the way, you can see it encounters all these kinds of routers that they each own have their unique IP address, but not all names, it seems. Okay. The amount of time as well it takes for me, my data to get from my PC to google.com. Trace is complete. And okay, it took that many milliseconds. So all in all, well, 1 second is all that's required for me to get my data. A lot of hops, but relatively speaking, lightning fast, to get from my data from Google, from me to Mountain View, California, or wherever the hell I am going to in google.com. If it's amazon.com, it's going to be somewhere else, okay, presumably. Okay, now what about all those other measurements of time above? Because, well, those ones, they represent the number of milliseconds or milliseconds it took for the process of data to go from my laptop to this router, to that router, to that router, to that router, and so on. And then, of course, it seems rather strange then it takes more and more time to get those close routers, but then it does to those further away. But then again, if I run this all day long, I would get different numbers constantly. Continually, because it depends as well to some extent on how busy everyone else is on the network. Other people on my network, other people at home, are they doing the same thing as me? Other people in the world, are they also at that given point in time? So routers, again, they're just CPUs, they're computes at the end of the day. Okay, they just are sometimes a little bit slower to respond because they're busy doing something else. They might be doing DNS caching, they might be doing God knows what other things, okay? But my data, it might get dropped in that context that we talked about before when we talk about TCP, UDP. It needs to be resent as well, which is just going to go and take some time as well. And I don't even have that. I don't have that information on screen. I don't see that happening. I can just make that out by nature of there being timeouts and so on. But it's a fair statement to say that this is going to give us a sense of the time and the ranges of time as well that it might take for me to go from Marco over here all the way to the other side of the world to Mountain View, California, in a matter of a few milliseconds. Okay, so all in all, like pretty fast, pretty fast. And even though it took me another moment to run the whole test again, that's why an email can be sent from your computer and it can be received nearly instantly by someone anywhere around the world because, at the end of the day, we're limited really by what? Speed of light. We're just pointing lights, we're redirecting lights in some other way. That's all it is. Well, to be fair, there's also hardware, there's cost and everything in between that, but you can certainly transmit our data faster than if you want a ticket in your hand and ran to the nearest border, right? Let's do something else. So I've got time. Let's go and push the boat out. Okay, well, let's take a flight, Chantel. Let's go further away this time. Okay, so odds are, probabilistically, Amazon's based in Seattle. They've got companies in North Virginia, which, by the way, just because of submarine cables makes it more sense, but Mountain View, California, for Google in that case, on the other side of the country in the US. But probably here on the on the East Coast versus the West Coast, there are also places abroad that are further away. I happen to be a use case of my own, but let's imagine most of you are in the UK. What's the furthest point away from the UK? What's a really far away country? 44. That's not a country. What's a really far away country from the UK? New Zealand, Australia. Okay. All right, let's try that. Japan, Hawaii. Japan. I know Japan is cheap. Yeah. Yeah. Okay, let's try one of those. Okay, Japan, Hawaii, South Africa. South Africa's a little bit close. Let's go really far away. So what we want to do is measure the same thing. But so what if we deliberately try to access a domain that is in fact abroad, that is really far away? So let's go home. Again, let's go trace routes. Let me go up on my keyboard in order to retrace that. Go back to the previous command essentially. And I don't know about Google, but let's go to. Do you know what's crazy? I found out recently. Speaking of Japan, I know BBC. Do you know BBC has a Japanese website? It won't be as dramatic if we went to New Zealand or Australia because they're English speaking, but Japan has a Japanese website and that's hosted there. So let's go ahead and check that out, shall we? So let's go to www.bbc.co.jp, Japan. So the domain name for that one that's for BBC's Japanese website. Please work. All right, the first hop's not loving me. All right, okay, but we're going to see a sequence of hops, which is good. So one after another, they're going to start to emerge. So the data is now leaving my computer, right? So I happen to be in Brazil. I'm working remotely, which is why the first one is coming from. By the way, I know Georgios, you're from Sao Paulo, you're from Brazil. You guys are obsessed with Japan. I was in Sao Paulo 2 weeks ago, and God alive, like you guys have such a culture. Yeah, I'm in Brazil right now. Again, one of the natures of working in tech is that you can work anywhere. So that's why I'm getting Brazilian news articles all the time. Yeah, it's cool. The beach was closed today, which is why I'm here. Anyway, so I'm going from my root servers in Brazil, which is Burr, and I'm trying to go to a Japanese website. As you can see, the sequence of hops here, one after the other, where my data is leaving my computer and in turn my local network, and then we're going to see some anonymous routers in between like that. So eventually we're going to get to 30, hopefully 30, just in the nick of time, because within which seems to be far more milliseconds already. Look at that, 126, 144, 212. How do I close the beach? It was raining today. That's why I said let's step in. So already I can tell that is an insane amount of difference. There's a huge amount. I was in I don't know how to call it. That street in Georgia. It's the place where they have all the food. It's full of it. You know the streets I mean, don't you, Georgia? In Japan. I was in Japan 2 weeks. I was in Sao Paulo 2 weeks ago for a convention, and they had something there completely unrelated to Japan, but there just happened to be a lot of people. I've never seen that many Japanese people outside of Japan. Seriously, I think by some nature of trade routes, I think Japan opened up their when Japan was a very closed nation under the shogun, I believe they were closed up by trading for about 200 years. The only one exception country. Does anyone know who they opened up their trade routes to? Japan opened up their trade routes to one country in Europe. It wasn't Thailand. They were honestly really horrible. They were horrible to people. Japan has had a really messy past. It was in Europe. It was in Germany. It was Portugal, Merrick. Yeah, you're right. So Portugal said, come right in. For some reason or another, you got on really well. I know it's just one of those weird coincidences of history. And then Japan and Portugal had a good thing going. And then obviously Brazil is kind of a halfway house between Japan and Portugal, if you look at the map, relatively speaking. So by some nature or another, I think that's why a lot of people end up in Sao Paulo, which is right there. So in order for me to get from Portugal to all the way down to Japan, you obviously had to go through Brazil, and that was it was part of the Portuguese Empire at that time. Anyway, back to the point, which is to say, we've now seen a market difference, at least from my servers, when I was going previously to the UK, Google.com. So for me to get to America, not that far, right? Because I'm on the same continent. I'm on the same land, you know. I'm literally here in Brazil right now. So for me to go to US West 2, whatever it is, from Rio to here, not that far. But in order for me to travel to Japan, well, you know, there's this big blue thing in the way. There's a lot of submarine cables in the way, right? So in this turn, there's a sequence of hops where in which my data is leaving my laptop, which is leaving another laptop and finding one to send to Hawaii or something. I don't know. But it seems to go from a fair few amount of milliseconds to, not that quick anymore. Right. And that kind of makes sense. If you think about that, it might take about 10, very, very quick, 10, 20, 30 milliseconds. And now it's in an order of magnitude more for me to get to the Japanese region, because that's not only a whole continent between me and Japan, but there's also an entire ocean as well. There's the whole Pacific Ocean. So those are transatlantic, trans-Pacific cables all around the world, submarine cables. All around the world that we can actually transmit our data through. Not to mention all the wireless technologies that we've evolved now today as well. So it stands to reason then that even though none of our routers were actually paying attention to me at that moment for privacy's sakes, this one actually indicates that for the last 200 milliseconds here or whatever, it got around the world rather digitally, rather slowly. And that does actually speak testaments and volumes about how latency works, okay? About how quickly those lower level primitives work as well. Everything we've talked about today, from TCP IP upwards to get to where we need to be, through a whole ocean and back in 200 milliseconds. The fact that you and I can have a connection and it's stable in real time, and I'm in Brazil and you're in the UK, it's pretty significant, okay? So together we have TCP IP via DHCP, and we can get all the addresses we need to actually put into the URL, the address space, the envelopes and such, and via DNS, can we convert those domain names into IP addresses and get back again? How about that? So those are the internet technologies, which ultimately are what governs how our data gets from point to point. But again, what is that data? What are those internet technologies that ultimately govern how our data gets from those places? At the end of the day, it's all just metadata, right? Information that gets our actual data that we care about from one point to another. It's the data that I care about. The contents of my email, the contents of my chat message, the voice message I'm sending, the video conferencing, the actual quality of our data stream right now, the contents of a web page. Those things matter to me as a web surfer, I was about to say. But the most popular service out there that you and I use every single day is just pulling up services, web pages, things online. I go through thousands of them a day, seriously. Just how many of them just pull up like that? So how is a web page, specifically this one, requested and received? Well, it turns out that when I type in HTTP, where's my pen? Why does that happen? So when I type in HTTP, we've all seen that before. So HTTP -- you've surely seen it before. Maybe you've typed it for some time, because chances are when you use your web browser, you just insert it in there automatically, even invisibly for you. It works, right? So if we try to get to, I don't know, Portugal.com, you just type in, look, I even said it. You don't say, go to HTTP whack Portugal or whatever.com, MrLion.com. I just type in MrLion.com, and my browser invisibly knows I'm trying to get to that, okay? So again, to be clear, HTTP is another protocol in the stack, which, let's go to that. Because your web browser, odds are I just inserted it there, it's another transfer protocol, okay? So another set of conventions, another protocol that web servers had agreed on a long, long time ago, the elders of the internet, to use when intercommunicating. So then, to be clear, what is that protocol? Well, you use it already. So Samuel, when you've can I ask how far in are you in your course? Have you completed your modules? Are you still have you got classes to come? Just to answer your question, because you'll find out. So as you progress, as when you do the later labs as well, you realize, oh wow, actually it's been Linux this entire time. 90% of the worst servers use. Come on. Okay, Samuel. Then you're gonna answer your own question in about a week's time. Yeah, look. So there's good reasons why we have Windows in front, and I still use Windows because it's more intuitive, it's a bit user friendlier, and it's just a bit more upgradable, shall we say? Without it's a bit more stable. I'm essentially catering to the devil and saying, I don't care, take my privacy, take my whatever. I'll accept all your bloat so long as it's stable, and I'm happy to do that trade off. Whereas Linux says, you kind of use cabbage for deodorant. You live off in a shack. You look beardy like Ted Kaczynski and say, we're kind of doing something new here. Now, to be fair, it's not used so much for day in or what we call a daily driver. The course, though, is an Amazon course, and we, of course, use a lot of Linux servers in Amazon. Sorry, I'm not answering your question properly. The answer is yes, but you're going to learn Linux by doing the course itself. It's supplementary. So you won't get an instructor that teaches you the stuff. Just like when I started, I had to learn the stuff kind of by myself. It's kind of supplementary to the course, but you can't sneeze without stumbling over a Linux tutorial here or there. Everyone's talking about it, and it's only going to appear the more and more you play around with an EC2. So an EC2 is powered by an AMI. I use Ubuntu, which is just another Debian distribution thereof. But there are many flavors out there. If you want to get into them, I would suggest you use Mint. Honestly, Mint Linux, minty fresh. If you've got an older computer, if there's something, of course you do, Laszlo. So if you absolutely hate yourself and you want to tell everyone, well, you want to have the street cred of saying I use Arch, then you need to sell yourself to the devil. Arch is, I've never used it, but by the sounds of it, it's horrible. It's horrible to use. It is the most complicated, gruesome thing. Actually, I've never looked at it. It doesn't look that bad, but that's probably just a Windows shop experience from it. Have you ever heard of Temple OS? Dinesh, I was just about to say it. Have you ever heard of Temple OS? As he says it in chat, Temple OS is crazy. If you ever want to go down a rabbit hole, look at Temple OS. It's a special kind of weird, really weird. Okay, so the programmer behind this creator here, absolutely nut job. He genuinely believed he was the second coming of Jesus Christ and built an entire operating system around that. Yeah, biblical theme, lightweight operating system. For some reason, it had this weird, wacky games in there that made no sense. A lot of graphical dead ends, a lot of dead spots. It had like this drone simulator on it. That was the homepage. That is the operating system, by the way. Yeah. Yeah, the first post is called Adam. It's all biblical themed. It's unusable, but it's fascinating. There's hundreds, thousands of distros out there. The one I like is called Puppy OS, because that's better suited for old computers, old bits of hardware, which it's good for old computers. Essentially, your grandparents. If you don't know what to do with yourself, get Puppy OS, because it won't live on today's modern day operating system requirements. The kernel just doesn't exist. Garda Linux has nothing to do with the Irish police, is it? Garda. Okay, it's again Arch based. Ooh. I can't actually tell what's the difference just by looking at the pictures alone. Okay, so it's gaming based. So it's got a KDE plasma. So as opposed to what I've been showing you is called GNOME, or KDE is another version. There's another called X Window, which is deprecated now, but this is about 30 years old, KDE. What we have though is a distribution built on top of that, or the kernel subsystem, which is just the new. Oh, what's this? Oh, okay, so it's another one of those wacky ones. Cool. So many out there. Honestly, there are so many different operating. It makes you realize just how obsessed people can get. And I agree. Kali Linux is probably the one that you want to get to. I have to learn it for what I'm doing at the moment, which is it comes. So nothing really different about it, but it rather just comes pre-built say, for example, when you install an EC2, for those that don't know what I'm talking about, when you download an AMI for your EC2, it already comes with all that software application software already pre-built. So by that same token, Kali Linux comes with a lot of penetration testing, sniffing tools, man-in-the-middle attacks, all those kind of hacking tools, shall we say, pre-built on there. So if you want to learn cybersec, if your OPSEC is leaning towards that, then yes, use Kali Linux. Honestly, I need to learn a bit. I actually need to learn it. So yeah, I'll come back to that. What was my point? Right, so HTTP. Deandra as well. Thank you. That goes as well to anyone. I'm seeing the time. It's 10 o'clock there. It's almost dinner time here. But if you do need to bunch off, then please feel free to do so. I'm not going to keep you behind. Thank you for anyone who's been with me as well. So, anyway, I've just got a few more minutes as well. I want to tie up the point with HTTP. If you need to go for bedtime, dinner time, feel free to do so. But I'm just going to wrap up the point of what HTTP is, okay? So it is just another protocol to get web browsers together. Sorry, which Linux distribution can you create on Amazon? All of them, Steve. Not all of them. That's a lie. So Linux 2 is a distribution that's based on Red Hat Enterprise Linux, which again is based on CentOS. So that one. In fact, if you go to the quick start, so the AMI menu, EC2 AMI menu, just have a look at what they offer. See, again, do you know how frustrating it is that every single page result I get back is in Portuguese? Anyway, I always have to go to the second one now. I've kind of tricked myself into doing that. That's an old version. Let's not do that. AMI options of Linux. So the best way to go is actually check the documentation. I don't want to pawn you off that way, but the one that we should be thinking of really is just Linux, Amazon Linux 2, just because of the stability of the platform. Yeah, but there's a lot of things. If you wanted to download anything else, you would do so. You would just download it as what's known as an ISO, an international standard organization, download it locally and figure it out yourself. There's nothing stopping you from doing that. I mean, let me throw the question back at you, Steve. Can you download, can you have a Windows-based EC2? Can you have a Windows-based EC2? I can, yeah. So that's actually one of the, so in answer to Sam's earlier question too, you do one of these, I think it's one of the last modules you do. We learn how to remote RDP into a Windows-based EC2, which is to say that we're going to connect like this from my personal PC, from my client over the network using an SSH key into an EC2 within which we have an EBS volume, which has an AMI, which is Windows-based. And once I'm in there, then yes, it looks a bit like this. So Windows EC2, it looks a bit like that. You have the same functionality as an EC2.
Atera is the IT.
Exact same functionality as a Windows machine, because that's what it is. It's a machine, it's a computer, it's the same as what you have in front of you. Just like you can have a Mac EC2, an iOS Mac, a Mac EC2. Same thing. And if you can go to this, then can you also go on Google and Firefox and Google how to download Mac or how to download Linux? You see, the whole point of a virtual machine is that it's completely isolated from the hypervisor. The hypervisor's job is just a bit of software whose job it is to carve up some of that underlying resources and instantiate a virtual environment which is completely isolated from one alone. So it thinks like a duck, it walks like a duck, it talks like a duck, therefore it's a duck. It thinks it's a computer, it treats itself like a computer, much ado like this one, thinks it's a computer. Now, in actual fact, it's not. It's just software mimicking a computer because I have given it all the required components, all the necessary hardware, but at no point was this ever real. Just like I can stop, start at any given point, and if there's a physical air gap between what I have on my desktop and what you see here. Currently, this is empty, but my documents are far from empty. I have tons of things. So there is a distinction between that. Therefore, I can go here and say, well, download anything. Kali ISO, just like that, and then I can download that on this particular virtual machine. It's just, yeah. Once you get used to one, you sort of figure it out for the rest of them. Pardon me, hiccup. Okay, so what the hell is HTTP? I love these discussions, by the way. Homework sessions work so well because it signals to me that you're actually listening, and I love that. So thank you. So the protocol, it's a convention. It just means, so what is a protocol, first of all? So again, a protocol, even though we might not call them much, It's a protocol. It's something that you and I agree on. It's a rule, MJ, right? So when I meet you on the street, MJ, I reach out to you and I shake your hand and say, hello, my name is Marco. And you tell me back, hello, my name is MJ. So we've established this rule, this protocol, this convention, this standard, this before upon agreed, this relationship in extending your hand and saying how, nice to meet you and so on. That's a human protocol that we've learned some time ago. And culturally, we might have agreed, generally speaking, that to agree each other on that manner. Computers, similarly in spirit, have standardized what goes on not only outside those envelopes, but also what goes inside as well too. And that's what happens with HTTP. So for example, if my goal at hand is to request a web page of a canonical website of a C name, say for example, let's go for example to HTTP www dot example.com. Okay. So, well, first of all, right there, something interesting happened. Okay, so something happened there. Let me just go back to Windows because it might be easier on to show. So let me go to HTTP again, HTTP whack example.com. So this is what we call the URL. A URL as a uniform resource locator. These days, your browser, whether it's Chrome, Safari, Opera, and the likes of that, it probably doesn't even show me the full information. If I just typed in Google example.com, it will get there too. But in a simpler, in the interest of UIs, browsers have started to hide that so-called protocol there. The HTTP is just invisible. It still exists. It's just invisible for you. So that you and I are just focusing on the host name, the middle part here, example.com, leaving you often sometimes with just mrline.com, the equivalent of something like that at the top of your screen. But if you click on that address, press enter, typically you'll see much more information down there too. And sometimes that information is just implicit, right? So now it turns out if I try to go to http.com or any similar name like that, you're actually looking for a very particular file on that server. But how do we reach that? So right there, it's changed. It's gone from HTTP to example.com. So that's what we know as the domain name itself, okay? As something that you buy, you rent, or the server itself is hosted on example.com by Amazon Web Services, that we talked about, by some Route 53, some internet registrar, or the likes of that, with all the associations of Route 53 that governs IP addresses or domain name service have been authorized to sell, or really rent in this case, to me or to anyone else, a domain name for any amount of time, usually in a 1 to 3 year rolling basis, for money. Okay, they're not doing it for free. No, what you might get initially out of them is renewable thereafter. So you might get a specific domain name and decide, I want to keep it thereafter. It might, be .com or whatever. For me, for my website, it's marcoverse.co.uk, and so on and so forth. So any number of hundreds of others of top-level domains that exist thereafter. And indeed, it is that suffix there that we're looking after that represents the type of the website. At least historically, that's what it is. Just like Japan was JP. UK is United Kingdom. .com for commercial. .net for network. .edu for education. .gov for government. Okay, so gov.uk, UK, United Kingdom. Of course, all those top-level domains are very well. Originally, it was a US convention, so US by design, which is to say that generally the Americans didn't have a .America. It was just .com initially. But of course, other countries ended up with what we call top-level domains, TLDs for short, country codes like, .Brazil, .br, and so on. Which is where I'm currently at right there. So whatever. That significantly, what they're going to do is they're going to signify to me what country that server is currently hosted in, okay? And though anyone these days can buy a .com, .net, .ninja as well, I've seen as well. But anyone can buy them, depends on actually who controls that particular suffix on Amazon.com. And then before, we might call that the host name, the name of that specific server that we're trying to visit within that, lives within that domain name. In other contexts, you might call that a subdomain, indicating what subdivision of a company or whatever that I'm trying to actually access. Do you? I/O, so I/O is a play on the in-out operations that a computer would do. And that's actually a good one to have. To get, as per convention in the tech namespace, you want to go for a .io because in-out operations, they're kind of cool. .pizza is also one as well. There was a story that surfaced a while ago. Pizza was one of the most expensive domains that you could ever buy. I think it's so expensive, no one owns it. Yeah, no one owns it. I'm just getting pizza places near me. Anyway, so if I don't mention that, basically via a slash, if I go to HTTP whack whack example.com / index.html, right? That implicitly tells me by, you might see the Linux file system, HTML, that / is something we saw in Linux just a moment ago. It's implicitly a file name, just like we saw with my system here. Uh, whatever. So LSLL. No, how can I get that? The file names. Yeah, I mean, so there we go. So for example, can you see the / there? That tells me I've just changed back myself to my home directory. That's what we're trying to do. And just like in the bin bash command, we're seeing there's a particular file in that bin directory. Again, that's all that the internet really is. It's human convention, but it's not required that the name of the file contains the web page that the server serves up by default. Usually it's called something called index.html, like that. Index.html, but it could be something else. It could be any number of things too, but that's the most common one by a country mile. If you don't mention that by a / it's just implied. You saw that on S3 static website hosting. It just says, by default, go to index.html. That's the default choice. It's any file, any file that you decide to put in that bucket that's implied or just explicitly said within that bucket. But the whole point of that point of information is to encapsulate the request of the page and actually of the web page itself. Because at the end of the day, it's HTML. It's it's an actual language in which pages are written in. That's inside the envelope, right? But it's being transmitted via HTTP, the protocol, the set of conventions by which browsers and servers both agree to send and request that information. All right. Oof. So, all right, yeah, I'm flattered. I was going to say I could continue talking about HTTP, but I think I'm probably going to burn up if I keep doing so too. HTTP by some convention, it looks like get requests / HTTP 1.1 and so on, where get is clearly just a verb by definition in all caps in this protocol. / meaning the default page for the website, the index HTML and so on. Right, yeah. So SEO or search engine optimization tries to lure you into the most crawled sites because if you're not on the first page of Google, you're dead in the water essentially. So then we've got the mention of, again, if I'm talking about the host colon here, when we're looking at HTTP message, just like this. So a put request, some kind of colon, there we go, host. And then we see there the port that we're actually working on there too, and the name of the host that we're actually looking for. Because it turns out that servers can do many, many things, not just Google servers with voice and chat and other services, but web servers can actually serve up multiple websites, example.com, thingy.com, linehub.com, so on and so forth. We can actually have shared tendencies, so to speak, on the same server in theory. We don't want to do that because of, we could do that, but let's not go into that. I have to say, I need to go and have my dinner. I'm being summoned. So I'm going to leave it there. I'm going to wrap up with that leaving thoughts. For the people that are new and have learned anything from that, and often a theme that gets thrown around a lot in this academy is if you come away learning just 10% of what anything's been talked about, HTTP, HTML are all new to you. Fantastic. Then I won't recommend you learning them. I recommend you learning HTTP superficially. Again, because you don't have to write the APIs. You're not a developer. You don't have to work as a network engineer. This is just underlying technologies, which are abstracted away from us by those low-level primitives as the network is just put into the cloud. So again, all that Amazon Web Services is just those old technologies of old, the things that we've talked about, the things that have existed since the 80s and 90s, just abstracted away from view, which is a good. So I'm learning my CCNA at the moment, which CompTIA is probably one to go through. So if you're interested in CompTIA, I think I put some resources online in the where did I put them? In the thingamajig. So again, if you're new to me, if you don't know who I am, I'm the guy who's always flooding the SharePoint. So where is that blooming SharePoint, eh? There it is. If you go over to the Job Club, look for this. Oh, by the way, I put some other handful of things. I've changed a few things. I put this on the foreground there because I thought they were interesting, they were useful. Open Guide to Amazon Web Services. That's a good one. That's a Git page full of all kind of things, all manner of things. Hand node diagrams, so on and so forth. So this is attributed to one guy. Jerry Hargrove, give him some love, show him some love. He builds up beautiful diagrams, which I have to say have helped me an awful lot in just conceptualizing a thing. Step diagrams, step functions, boom. Talked about AC2s today, boom. Transcribe, quantum ledger database, text extract, and so on. Good hand-drawn diagrams. Periodic table as well. I've also got that as well too, if you just want them at a glance. Again, just go through these. There's a handful of things there too. Corey Quinn runs this page. He's very funny. I find him very entertaining. Very, very funny guy. Just subscribe to him. His podcast, his old newsletter is fascinating. Very funny guy. What else? Yeah, if you're a Kindle reader, I'll put that there as well. I'm learning, well, networking stuff is there if you want to learn. Yeah, you know, other stuff that's kind of emerging here and there. The whole point of the SharePoint is just to have student-led resources. So Najma, that's the SharePoint which you will know and love. I'll just put the link there. Absolutely. And Samuel, not everyone's going to be passing their exams. In fact, you're going to get people. I've been here for over 2 years now. Some people have been, and I came from an absolute beginner's background. I came not knowing how to do anything. So the fact that you've been in 3 weeks and you've been able to follow this conversation along is a testament to how far you're going to come in about a year's time. Okay. I believe, Ada, you will have access to this by nature of just being here. By enrolling in the course, you will have had to have provided your email address or that credential to Mr. Beldine. Say, Andy, what's up? Gimme. He will authorize you into the participants list. But you should have this. It's surprising me that you doesn't. If you don't have this, I don't know how you got here in the first place. This is just the homepage. It's the Academy homepage, which is to say, if you don't know what that is, next time you go to a class, bully your instructor. Just get him to be to put you on there. In terms of the CCNA and Cisco exams, though, go over to the Knowledge Hub. So in Job Club, you're going to find the Knowledge Bank, where in which I put in resources I find helpful, including the Cisco. Well, I think I put it under networking. Yeah, so CompTIA, CCNA, that kind of stuff there too. Side of subnetting and so forth. You're going to find a lot of things there too. Yeah, cool. But Samuel, don't freak out, okay? Because I can already see the cogs turning in your head. You're thinking about exams, and I tell you, buddy, that's the milestone of the end goal. I really seriously mean that. I passed my CCP within a month, and I knew nothing. I genuinely felt like I was an imposter for the best part of a year because I rushed the exams and I didn't get anything out. Yeah, I could tell, Laszlo. I thought so. I thought there was a Cisco bit of pedigree in the room tonight. So that's good to see. Again, Amazon. I sound biased, but there's more to the world just Amazon. It's the biggest and the most important cloud provider by a mile. But it's just abstracting away the data center, you see, and the data center technologies are what you're studying with Cisco. So yeah, sorry. Najma, please go away. I'm gonna end the session. I'm being rude by keeping you behind. I'm just kind of contextualizing some other shared resources and so on. So yeah. Thank you very much for your attention. You've been brilliant. And be sure to have your veggies. Victor, good to see you. I didn't see you there this evening. Good to see you, buddy. My man, amigo. Okay. Let's reconvene. I'm flattered. It's been a while since I did one. I think I've got another one next month, so we'll do something else there. Okay. I think you've got I don't know who's on this Friday. Calendar's not out yet, but we'll see soon. Anyway, be back on Friday. I'll probably catch you here or there too. Thanks again, everyone. Take care. Take it easy. See you all soon. Good night.